So thank you everyone for joining this session, ACI vPod, providing secure network policies for classical Ethernet networks. Wow, who came up with this title? It's so long. So obviously the focus of the session will be ACI vPod, and V stands for virtual. So before going deep dive into what vPod is, the architecture, we're also going to focus on how ACI can bring value in the cloud, because we know that today in modern data center, the data center physical location doesn't really make any sense. The data center is basically extended everywhere where your data is running. So public cloud, private cloud, can be container, virtual machines, basically everywhere. So we're going to focus on this in the first part, take a little look of the cloud evolution, cloud history, where we've been coming from, the various flavors of cloud, the consumptions model, all these kind of things. It's important to get all this history and background to be able to position and understand the various ACI solutions that are part of the ACI Anywhere messaging. So just quick show of hands, how many know a little bit about this ACI Anywhere message? Right, okay, almost everyone, so I'm not going to spend too much time on this. So vPod obviously is part of it. So we're going to analyze the different use cases for vPod, because you don't want to mix vPod with other solutions, such as what we're doing with AWS extension, for example. It's not the same use cases. Then we're going to go deeper into the vPod architecture, how to deploy vPod in your network, what's the different steps, what is involved in there. And finally, we'll go in packet walls. So I've got like probably 3-4 use cases for you. Should take about 20 minutes. I'm trying to make it like on time because yeah, it's 1.5 hours. So it means I won't cover AVE, which is one part of vPod. I'm going to focus on the infrastructure part of vPod, but I will go deeper on AVE if you're interested on Friday morning. I know it's, I don't know, probably it's bad karma for me. It's like I've got the last session of today and the first session on Friday morning, which is not ideal, but yeah. It's called ACI for VMware admins, and I will cover AVE, like the virtual machine, the service virtual machine, AVE in more details. Okay, so usually when I'm talking to customers for the last couple of months since we've been releasing this ACI Anywhere messaging in marketing umbrella, one of the first questions I'm always asking first is, okay, do you guys already use cloud? And cloud means very different things for different people. I've got some people who's telling me, yes, we're using cloud. Basically, we have our email service, which is Gmail. Okay, this is not what I mean by cloud. Some other people may say, look, we're using Salesforce, right? Okay, no, this is still not the case for me. Some people may use just EC2 instances. So basically, depending on the situation, yeah, this quote may be true or not, right? There is no cloud, it's just someone else's computer. But I guess this sentence may be true in some cases, depending on the consumption model we're using cloud. It can be, if we look at the cloud history, let's say 10 years ago, the foundation for cloud was really, if we don't consider public cloud for one moment, right? The very beginning, when companies like VMware and others were starting to talk about cloud, it was more about what the hell is going on? There is this, I've got an infrastructure that is virtualized. How can I start building a cloud based on that, right? So if you look at the definition, the basic definition of cloud, the foundation is really about having a set of a pool, or actually the infrastructure resources that can be put together into pool of smaller resources to give you more flexibility and more agility, and then you can start building some automation on top of it to build services on top of those infrastructure resources. And this is what we know as infrastructure as a service. So that was one of the main foundation for cloud. And obviously, the people provisioning this service was IT. So typically, you had a virtualization engineer working on a VMware platform that was using vCenter, vSphere, and building some sort of automation to be able to deliver some sort of services with specific requirements, such as elasticity, scale-in, scale-out, all those kind of definition for modern cloud. But essentially, that was infrastructure as a service, and it was managed by IT. So as cloud evolved, there was different sort of cloud. Not only infrastructure as a service, but things like software as a service. Like here you can see people consuming, like I was saying, Office 365, Salesforce, can be Gmail. So it's more like the end user. So the people responsible for this consumption is usually the line of business. It's not the IT anymore. In the same way, you can have developers who don't want to be constrained by I would say the speed of innovation of IT, which sometimes is a lot slower compared to public cloud innovation, right? I mean, by consuming directly public cloud services, you also can leverage their innovation, right? You're not tied to your internal IT service innovation speed anymore, right? So obviously, this led to some unfortunate situation, things like shadow IT, where basically the developers were so using their credit card, the company credit card, to pay, Amazon EC2 instances and start working on this. So the consequence, obviously, for IT is that they're losing the control. And at the same time, part of the infrastructure pool is not basically located on the premises. It's not infrastructure pool, right? The IT is not responsible for that. It's basically the public cloud provider who's delivering these resources. And as I said, IT tend to lose control over those kind of environment. So this is where we started to see the rise of hybrid cloud, because hybrid cloud gives you the ability, or actually the concept is really about having the ability to connect your on-premises infrastructure to various public cloud and leverage the same benefits, right? And ideally, what you want to do is enable the developer there to, whether they go on-prem or in the cloud, they can leverage the same services. So typically, they say it would be like you go on AWS, you can use Beanstalk as a platform as a service type of service, OpenShift. They can go to Amazon, deploy EC2 instances, but more importantly, IT teams should be able to provide a control process for all those provisioning and manage this life cycle, right? And another benefit of hybrid cloud is that by having these changes, the process changes in place, then you can seamlessly take one application from your public cloud, take it as it is with the native construct of those platforms, bring it into your data center, and basically provide the same service. So from the developer point of view, whether they provision this on the public cloud or in your on-premises private cloud, that doesn't make any difference. That's basically a seamless experience for them. They don't have to modify anything. And that would be in the ideal world. But we know that depending on the solution you use, it may not be the case. And this is particularly true because of the network. Right? How do you manage the network in this type of environments? Because public cloud, you may access it via VPN, you may have multiple VPCs. How do you manage connectivity? How do you make sure that your security policies are applied regardless of the location? Right? Those are current challenges because not only you have VPN, but you may have remote offices, you may go through one. So that's a heterogeneous network that you want to make sure that you have the policy that is applied across the board, right? So you want to avoid to manage all those VPN individually, have many VPCs, go to AWS, specifically configure security groups, and then go back to your on-prem environment, maybe configure some physical firewall, ACL, all those kind of things are quite challenging in modern data center. Right? Another requirement of modern, or hybrid cloud or modern platforms is scalability and elasticity. You want to be able to scale in, scale out, depending on, depending on the team demand, and quite often it's very difficult to keep track of those changes in the network. it's very hard, let's say you add an application, if you want to add a firewall between tiers of this application, and the developer at some point decide to decommission in that application, right? Decommission that application, how do you remove the rules of the firewall? How many companies can guarantee that the current state of the firewall effectively represents the security requirement of the application? Usually you have still rules in all the firewall that any security admin is afraid to delete because he doesn't know what will be the impact, right? So this is quite challenging as well. So what are the consequences for the network? And this is also where ACI may respond to some of these challenges. So as I said, you need to be able to provision connectivity, security on demand in a consistent way, regardless of the workload location, right? It can be on-prem, in public cloud, or in private, in a bare metal cloud. We're going to treat those use cases with vPod, right? Another big requirement for the network is, because we have so many constructs to manage, we don't want to expose all this complexity to the network admin or to the end user. So that's another requirement, is to, I would say, abstract all those low-level constructs into more simple to consume policy model, right? And finally, one key component for, I would say, this modern network, interconnecting all those clouds together, is obviously programmability. Right? API today is a key requirement for a network to be programmable. Right? Then you can use any language, you can use any scripting to program this network. Right? And what I'm saying here is basically what I'm describing is all the, as you know, ACI, right? So how many of you knows ACI deep dive? I mean, okay, well, I'm not going to go what ACI is. So basically what I'm describing here, as you could have guessed, are the characteristics and the features of ACI. So, so far, you know ACI probably in the context of multi-pod, maybe multi-site, but essentially you needed a physical fabric. So making things a bit harder when you don't have the Nexus 9K in a data center. How can I extend my policy if I'm using like AWS or maybe a remote data center or a colocation facility? Right? So effectively, ACI will help transition to a hybrid cloud model and bring an agile network for cloud-native application, but also, most importantly, still maintain this SDN function for your traditional application. And this is all the secret of hybrid cloud. Hybrid cloud is really there to be able to satisfy both sets of requirements. You want to give your developers or your application owner the agility and the benefit of cloud-native applications, so using containers and all the DevOps way of managing application lifecycle. But you don't want to forget about your legacy application, which is probably more, they will stay for a certain period of time into your on-premises data center. So you don't want to forget them, right? So as time, over time, obviously the goal is to migrate those, when it's possible, those legacy applications into a new cloud-native application using container. And as I said, then you fall into the model where, regardless of if you want to do it on-prem with ACI or in the cloud, for the developers, the experience will be seamless, right? So they can develop with Kubernetes native policy in AWS or on your on-premises data center with ACI, they will use exactly the same policy that will be ingested into ACI. That's also one key component. Okay, so now I want to describe a little bit the difference between vPod, or more to situate vPod into the broader messaging of ACI Anywhere. So what is really key to understand in the different contexts. So in ACI Anywhere, so we have remote live. We also have, and that's the topic for today, vPod or virtual pod. We have multi-pod, multi-sites, which is basically the context where vPod will be running or AWS extension will be running. So every solution we build can be classified as a multi-pod solution or a multi-site solution. And this is what I want to explain here. So what are the different contexts? So multi-pod versus multi-site. The main difference, as it's stated here, in the case of ACI multi-pod, you have a single APIC cluster that is managing distinct fabric, but logically treated as a big single fabric, right? The difference with multi-site is that multi-sites, you will have distinct fabric, but managed by different APIC cluster. So from an operational perspective, when you connect to your fabric, you only see, let's say, this fabric, right? You don't see this one. In multi-pod, because you have a single cluster, if you connect to this fabric there, to the APIC there, obviously you will see the resources in the same cluster, right? That's the main difference. So this one on the left is more for HA and disaster avoidance. So typically, if you want to build your, let's say, your VMware cluster, this would be a stretched VMware cluster, right, with a single VDS that is spread across multiple physically separated locations, right? Multi-sites is more for disaster recovery, where you would use any tools like Zerto or VMware Site Recovery Manager to recover your workloads at the destination. So typically you have one VDS, one vCenter, another VDS in the second site, and you can do true disaster recovery with distinct fault domains, right? So that's the multi-site type of approach. And then you can also combine both. So you can do multi-pod. So here we go. You have an APIC cluster with pod 1, pod 2, and then also have a one that is connected a second site back to your primary site. So you have site 1 in that case that will encompass pod 1, pod 2, and then site 2 with a single pod, right? And you can run, obviously, VXLAN extension. You can flood across the, the WAN and the IPN, providing basically, layer 2 extension. Or you can choose to limit the flooding as well, right, on a per BD basis. And this is quite unique in multi-site. On a per BD basis, you can selectively enable or disable flooding for a particular layer 2 domain. So, before going into vPod, the second solution that you don't want to mix vPod with is AWS extension, right? So AWS extension, the cloud becomes a site, okay? So what that means is that APIC won't manage AWS, right? You need, as in multi-site, right? Because that's a multi-site architecture, you need the multi-site orchestrator so that you can synchronize the policy between your on-prem data center and into AWS, right? So by using the multi-site orchestrator. So, and basically, I want to start with what vPod is not today. So first of all, this is not for public cloud, right? For public cloud, this is what I just mentioned. This is a multi-site architecture with a cloud APIC. That's a different architecture, right? So the idea of vPod is not to run on public cloud. For public cloud, that's a different architecture where we will be using native cloud constructs, not vPod, not ACI in the cloud. We don't build overlay in the public cloud, at least at the moment. A second thing that vPod is not today, right, this may change in the future, is a total replacement for ACI. So although it's virtual, it still requires a physical fabric somewhere on the network. So you need first your physical pod, and then, once you have at least the main pod, you can start building virtual pod as a second pod, right? And then, obviously, the third one, today, vPod is not combined with a site, right? So it's not a site by itself. You don't need the multi-site orchestrator, which means that today, when you build your main pod, so you deploy one ACI fabric, you have one APIC cluster. And this will be this cluster that will be also responsible for the deployment of vPod, right? So it's more the HA/disaster avoidance scenario. It's not a true disaster recovery between your main pod and your virtual pod, right? So, oh, by the way, if you have any questions, just feel free to interrupt me. We have a mic there, and I've got maybe my colleague Domenico somewhere there. No? Okay. never mind. Yeah, there is a WebEx also team space that has been created. So if you have any questions, we can also follow up on Teams for a couple of days, I think. So the main use cases for vPod, right? Because what is left now, right? So there are three main use cases. The first one is you have an existing non-ACI environment where you want to extend your ACI policies. So it may be because you just acquire new switches that you don't intend to replace, or it may be because, and that's the second use case, where you have maybe a smaller data center where you don't want to replace the hardware, right? You don't want to have Nexus 9K there. So vPod, yeah, may be a good alternative. And then there is the third use case, which is more about addressing the co-location challenges and the bare metal cloud. So what's the difference between bare metal cloud and public cloud? So public cloud, typically this is AWS, GCP, and any other Microsoft Azure, any other the big ones, right? Bare metal cloud is more something like IBM Bluemix or any third party like Dimension Data Cloud, all those type of cloud where you can bring any type of host. And in the case of vPod, obviously, today we're running only on VMware vSphere. So what vPod is requiring is that at some point you need to bring up some E6i hosts, right? So this is typically the use case for bare metal cloud, right? When you have the ability to deploy E6i hosts, right? So, and one idea of vPod is to, not limit you to a single virtual pod. So you can mix and match the different use cases. So in one data center, you may have like a co-location or small remote data center. Another use case may be you're in a brownfield environment where you have started replacing the switches, let's say with Nexus 9K standalone, but you don't want to install, to replace them or to install the ACI image on those switches for various reasons, right? So this is where ACI vPod can become very handy. And yeah, as I said, the last use case would be if you want to mix also like a hybrid cloud, but extending the policy to a bare metal cloud into your environment. Okay, so now let's go a bit more deep dive into the architecture. So vPod has mainly three components. So the control plane itself is composed of vSpine and vLeaf that are virtual machines, and I'm going to describe in detail the different characteristics. The important thing to remember about vSpine and vLeaf, they are not in the data path, right? They are just there for the control plane. So when data is flowing, they are not going to vSpine or vLeaf virtual machines. There's no things like performance consideration for those machines. There is just like latency, but I've got numbers on latency as well. And I would say, so vSpine, vLeaf, and then we have ACI Virtual Edge, or AV. So who knows about AV a little bit? Okay, some of you, right? So the goal of AVE is really to be the data plane, right? So obviously, we had to change AVE code to make it work with vPod, because AVE as you know it, or the Nexus 1000, so who knows Nexus 1000V a little bit? More people. Okay, so that's the same sort of concept, right? Except that in a standard ACI environment, AVE or AVS, when the support was there for VM kernel, the goal is really to create a distributed stateful firewall. That was the only goal of AVE/AVS, to maintain like a connection table. But all the policy was still enforced as the top of rack leaf, right? Not inside AVE. So obviously, in a vPod environment, you don't run ACI hardware, right? So you need, at this stage, to enforce the policy inside AV. So what that means is, as you know, ACI is working by using overlay between the different top-of-rack switches, and we call it iVXLAN, but it's just standard VXLAN. We just use extra information in the VXLAN header to transport things like the source class and information if the policy has been applied, all those components that are required for us to enforce the policy. So instead of using normal VXLAN, as was the case with AVS or AV in standalone mode, vPod implements a full-fledged leaf inside AV so that we can do the distributed default gateway in AV as well as security enforcement. So that's the main changes that we have introduced for ACI 4.0. This is this version of ACI Virtual Edge. So it's the same image, it's just that at deployment time, it will implement the functions or not, right? Depending if it's a standalone or vPod mode. So two things, right? Data plane on the one side, and then IVXLAN for the data path, right? So in terms of the VM characteristics, the idea is to have like 2 vSpine. You don't really need more. It's just that you need 2 for, obviously, availability. So there are 2 vCPU, 8 gig of RAM, 80 gig of storage, 2 vLeaf, which is, again, 2 vCPU, same thing, 8 gig of RAM, 80 gig of storage. And then that's it for the control plane. And AVE, it's 1 per host. So AVE is basically a service VM, like if you know about Nutanix, it's the same sort of approach where you build 1 service VM per host so that we can redirect all the traffic on that host to that virtual machine, right, for policy enforcement. So there are a couple of requirements. So supported spine. There is still some hardware dependency, right? Because you need a physical site to implement your main pod. Today, we're still under discussion. Will we release a full virtual ACI version at some point? Yeah, I don't know, maybe. I think we should definitely do it, but still under discussion. So you need like latest generation spine, so EX spine. At least one of them, right? You can mix and match your spine. You don't have to connect every spine to your IPN network, but at least I would say 2 need to be connected for redundancy. APIC 4.0, where so vPod was limited availability. Now in the MR1, so the maintenance release, we have made it general availability. In your vPod data center, you need vCenter 6.0 or later. And then the rest is really about best practices design, where if you look at VMware VVD or any VCDX type of design, you don't want to mix your payload cluster with your management cluster. And typically, you need at least 2 hosts for each. And what you would do is run the control plane of vPod, so vSpine vLeaf into your management cluster. And AVE, for sure, you will run it into your payload cluster. So this is why you have those two clusters. But obviously, if you're for smaller customer, you could mix everything into a single cluster. But then you have to be careful not to fall into a chicken and egg issue, right? If you lose the network on AVE and you also connect the control plane on it, that doesn't make a lot of sense. Now, the important part is how do you deploy it, right? We didn't want to leave people do this manually. You don't want to go on every host, every ACI host, deploy AVE manually. You don't want to download vLeaf, vSpine, and again deploy and configure manually. And you don't want to basically go through the vPod/multipod configuration manually either, right? So, and this is what we are going to talk about now. So the first thing we do, as I said, we support now the latest number. There are 6 vPod for in any particular fabric, but we hope to increase this number to match multipod number, which is currently, I'm recorded, so this is 12, right? Thank you. 12 pods per fabric. So the idea is to support also vMotion between your physical pod and your virtual pod. Because remember, because we are in a multi-pod type of context, it means that by default, we keep the same VNID for all the VXLAN across the board. There's no need to translate VNID like in multi-site or to enable anything, right? By default, because we use the same multi-pod architecture, which means that in the overlay, we have BGP EVPN running not between spine, but between virtual spine and physical spine, so that you can advertise your EVPN route, so type 2 route, so you can have MAC address, IP address, and populate the kube database. So who knows about kube database? Okay, so I won't go through it too much. I mean, not explaining, but I'm going to explain how we maintain COOP in sync without explaining what COOP is. So basically, yeah, BGP would be the control plane, and VXLAN would be our, or iVXLAN, should I say, would be our data plane. Right? So you have full extension when you need it of bridge domain. Now, a couple of things we don't support yet. So those are items on the roadmap. So today, we don't support multi-sites with a fabric where you have vPod enabled. I've got it in my lab, it's working, but yeah, it's not supported yet. We don't support in conjunction with remote leave. So I don't know if you, any of you went to Mac's session on multi-site? Okay, maybe, I think he talked about remote leave a little bit, yeah? Yeah, also. So we don't support it in conjunction with remote leave. But obviously, we support it with multipod. And basically, this is all my screenshots and the deployment I'm going to show you are basically an extract from a use case where I have 2 pods. So there's 2 options. You can start with one main fabric and have a second pod, which is vPod, or you can have existing multipod, so with 1, 2, or more pods, and then add a new one, which would be vPod. Okay, now if we go a bit more in detail in this architecture, what are the different components and how are they communicating together? So let's start with this on the right. So you have your on-prem data center, physical leaf, physical spine, connecting to an IPN, like multiple way of doing things, so far so good. But then on the vPod data center side, what do we need? So if you think about it, right? So we have here on the management cluster, vSpine, vLeaf, and basically they are virtual machines. So they are, you have to think about them as normal, any virtual machine, which means they need layer 2 connectivity, they need a default gateway, and this default gateway needs to be able to talk back to the IPN. And because we are going to establish a overlay, a BGP overlay, we need to use this underlay to enable or reachability between all those components. When we have reachability between the physical spine and the virtual spine, then we can build the BGP relationship and start exchanging host routes, right? So what that means is because those guys here are basically your layer 2 construct, IP addresses and MAC addresses, they need a default gateway, right? This default gateway will be residing in your vPod data center, right? There's no ACI in this remote data center. But you need a default gateway somewhere, so we call it like the vPod gateway. And this guy there basically, that's typically an SVI, that it needs to participate in whatever protocol you're using. So here, it's any protocol, but on that side, obviously, you have to have OSPF, like in multi-pod connection to the IPN. On this side, it can be anything, but let's assume you do OSPF. Then this SVI there, acting as a default gateway for vSpine, vLeaf, and AV, should be just a passive interface, but just there so that you can establish the peering relationships across the board, so between your vSpine and your physical spine, right? So we'll see there's a couple of other requirements, but mainly you need this gateway somewhere in this network so that vSpine can talk back to your data center. And when we have this in place, it's just BGP between vSpine and the physical spine. Now, in terms of, that's for the control plane. So 2 interfaces, one which is the vPod infra VLAN. So it means that this is, as in normal ACI, you have, so in normal ACI, you have this infrastructure VLAN, which is the VLAN that you extend if you want to talk to other devices, take control of other devices to participate in ACI. It can be things like, if you're using container, we're using OVS, that would be the infra VLAN transporting all the VXLAN frames, right? So here it's exactly the same VLAN, except that it's a normal VLAN. There's no ACI fabric, right? It's just a VLAN that you will deem as infrastructure VLAN. So basically it can be any VLAN, right? It's just that this VLAN will be the one corresponding to the SVI there. Right? It's just that. So your infra VLAN, which is locally significant to your vPod, and the second interface is the management VLAN, so you can manage just vLeaf, vSpine from an out-of-band perspective. That's it. Now, from an AVE perspective, there's a little bit more. right? Because remember, this is a service VM. So all the traffic that goes from the VM to the physical NIC of your ESXi host, so all the traffic going out from the host, from the host to the outside, and all the traffic coming in needs to go through AVE, right? So we need two interfaces. One internal interfaces into AVE. This is where the VM will talk. So on this internal interfaces, this is southbound communication between virtual machines and AVE. And then we need an uplink, right, between this VM and the physical link. So typically, the internal interface of AVE is not tied to any physical NIC on the host. It's just there, not connected to anything. But the northbound interface of AVE, this one is tied to a physical link, and this will be this link that will transport all the VXLAN frames, right? And obviously, because this is VXLAN, we also have the VTAP termination happening in AVE, right? So what you end up, effectively, on the vPod infra, so this link, you will enable VXLAN communication. Right? So before going into the data plane, just wanted to have a quick word about the control plane. So why we have split the different functions into the three components. So one question I often have from customers is, okay, why did you separate vSpine from vLeaf? Why didn't you do just like a single virtual machine or a couple of virtual machines with all the functions? So the answer is really easy. It's because of scale. Because ultimately, the vLeaf will be responsible for the deployment for the IP addresses allocation of all the AVEs. Right, so we want to scale horizontally this way. So like a set of vLeaf will be responsible for a set of AVEs. Another set of vLeaf will be responsible for another set of AVEs. Right, so this is why we have decoupled vSpine from vLeaf. Right? And also, if you're familiar with the notion of Opflex, so if you know a little bit, I don't know, maybe OpenStack or even AVS. So Opflex is the protocol we are using to talk to the southbound devices, southbound switches. So for example, if we want to program OVS, this is the protocol that we are going to use, right? So Opflex come always in pair. In a physical ACI fabric, you have the Opflex agent running on OVS, for example, on the virtual switch, and you have the Opflex proxy that is running on the leaf, on the physical leaf itself. So it's like a client-server type of relation. The same thing happens here. You will have the Opflex client inside AVE that will be responsible for listening to specific switch events. If a new VM has been spinned up on the environment, Opflex agent will notify Opflex proxy, and then you will be able to download the policy to the switch, right? So we need this two relation there. The second one we need is the kube citizen and kube resolver. So it's like a normal ACI. You have the kube database that is shared by all the spine. Here it's the same. Kube server or resolver will be on the spine. And the kube client, which will be responsible for managing local endpoint discovery, will be residing on AV. And for every new entry that you have here, it will update the kube database on the vSpine, right? So locally, you attach an endpoint to your ESXi host. When it talks on the network, we use normal learning behavior from ACI, populates the local kube database to the spine, right? And then we're going to see how we synchronize the vSpine to the physical spine on the main site, right? And then the last one, which is probably also very important, is the vSpine is acting as a route reflector and the vLeaf as a route reflector client, which means also that we have to decouple those two functions on different elements. And the role of this is exactly the same as in physical ACI. It's basically to distribute one route. Right? It's just this, right? So those, basically, if you learn something on a border leaf in the physical ACI site, it will be reflected in BGP, and BGP will install the route into the vLeaf, and in turn, the vLeaf will generate a kube message to update the kube database upstream in the vSpine, right? So basically, if you know ACI physically, that's basically the same concept. It's just that we have organized things a bit differently. OK, now this is the hard part. The thing is, with multipod, so this is what I'm going to be talking about is an environment where you already have I took like the most complex things you can deploy. So that's an already existing multipod environment. And then you want to add virtual pod in this type of environment. So now we're going to see what's the different addresses that are needed. But you can, I mean, the wizard takes care of this for you. So you're going to end up just filling a couple of IP addresses, subnet, range, and it's going to populate everything for you. But it's important to understand the philosophy behind it. Right? So typically, so everything is in green is the multipod TEP addresses, so tunnel addresses. So first of all, we have the control plane ETAP in multipod, which is the TEP used for BGP peering with the remote spine, right? We have then the data plane TEP, which is I think I have some, yeah. So this is the, first of all, before going into the green one, when you install an ACI fabric, right, you have to, the first time you provision APIC, you have to specify a TEP pool, right? This TEP pool will be allocated, I mean, the TEP from the leaf and the spine and APIC will be taken from this pool for the different IP addresses, right? So classical, day one ACI deployment. Then, as I was saying, the control plane ETAP is a loopback IP address, and it will act as the spine router ID for MPBGP VPN peering with the remote spine. So that's the control plane, right? BGP peering. It's on a per spine basis, and obviously it's advertised in the IPN. Then we have the data plane tab, which is shared by all spines within a particular defined pod. And it's used as a next hop in COOP for traffic coming from remote pod. So typically, when you install the COOP entry in the remote spine, the next hop will be this Anycast address there. So we can provide load balancing, basically. So that was for physical pod, when you have at least two pods. Now, what do we need in vPod? We're going to be, it's a bit different. So we need a new TEP pool for vPod. So you specify just like a normal subnet, but within this subnet range, you will need to specify a reserved sub-range, so within that pool, at the start or at the end. So we recommend like the last or first 8 addresses. And why you need this is because we cannot really control like the devices that you want to include into this infrastructure VLAN in vPod. So typically, you may have HRSRP IP addresses. You may want to have a DNS. And then on top of this, you need the gateway IP. And this is where the vSpine and vLeaf router ID will be taken from, right? So this is only 4 of them. So this is the sub-range within that pool that you specify. And for the rest, it will be taken automatically from that pool. And the rest is basically, we're going to see the HREPs, which is the multicast TEP address, and all AV IP address. So again, the difference is that vLeaf, vSpine will get their IP address from APIC, right? But AVE, all AVE will get their addresses from the vLeaf, right? Because we want to manage AVE locally. You don't want to go through the one back to manage the IP every time you deploy a new AVE to manage those DHCP requests across the board, right? So this is what is required there. Second address, so we're going to go up, HREP TEP. So this one is headed for headed replication. Basically, any packet or frame that comes as a BUM traffic to vPod needs to be replicated. We don't use multicast in vPod. We use headed replication. And we will elect in that particular vPod 2 AVE responsible for replicating the frames within a vPod, right? And each BD that you deployed will be associated with one of these AV, one another, right? If one fails, the other will take over, right? So basically, yeah, it's used as a destination when you have traffic from physical pod coming to vPod. For all bump traffic, it will be used as a destination TEP, right? Or from another vPod. So vPod to vPod will be the same thing. The control plane ETEP, again, the same principle as in multipod. This will be one TEP address per spine. So this is allocated from the reserved subnet. And it will be used to establish BGP peering with the physical spine, right? And yeah, this is also what you will see as a router ID, right? So the whole TEP pool there will be advertised inside your IPN, right? So by default, this is what will happen. And then the last one, which is not really used, but is still there from a, I would say, multipod legacy. So the data plane TEP in vPod, I think it's configured automatically for you as well, is just an Anycast IP address that is used for all the, shared across all the spine. It's used as a BGP next hub for type 6 EVPN routes and BDGPO, which is just basically multicast traffic. So that was for vPod. Now, this is what is new, I would say. And if Max talked about remote leaf and what we'll be doing, this is the same principle. So why are we doing this? So the first thing is, remember back in the day when we first released ACI, we were saying, yeah, pick whatever IP range you want for your TEP pool. It will be never routed on the network, right? Guess what? Now it has to be routed if you want to do vPod. And potentially, you may not be able to create your own VRF in intermediate devices. So we were like, OK, let's provide some NAT functions, something like that, so people can basically won't have to scratch the fabric to reallocate a TEP pool for applying, for deploying vPod or remote leaf. That's the same thing. And this is what is in red now. This is why I've put like some transparency, because it was a bit messy. So now we call it the external TEP pool, or you may hear people also talk about routable TEP pool. That's the same thing. So this is a new TEP pool, and it's only used for physical spine, APIC, and border leaf, right? So because in vPod today we don't support local layer 3 outs, which means that from AVE, we need to establish a tunnel to the border leaf in the physical site, right? So this is why, at some point, this address needs to be advertised on the network, right? So that we can use the layer 3 out from the physical sites. No local layer 3 out in vPod today. And then APIC, because you need to get connection to APIC to get the IP address from DHCP to vSpine and vLeaf. And obviously the spine, right, because they need to establish relationship with BGP. So let's go. So it needs to be routable to the one. The entire prefix will be advertised. It can be, the mask can be between /29 and /22. And basically this is a source NAT address for, as I said, APIC, spines control TEP, and border leaf nodes. So that's not that many addresses, but still, it needs to be, if you have planned for a routable, already today, TEP pool on your network, I'm sorry, I can't do anything for you. You still have to use this one to configure this extra TEP pool, and one per pod, right? So now you have, so imagine here, we had like an existing multipod, which means that you already have a control plane ETEP there. Now we're adding a routable control plane ETEP, right? So if you do a show interface on your spine, you will see a new IP address there that is used for BGP peering with vPod spine, and it's automatically allocated from external TEP pool range. And that's the good news. You don't have to configure those addresses manually. You just specify the pool, and the wizard will do the rest for you. But it's important to understand what's happening behind the hood. Then this is the bit that is depending on whether you have already multi-pod or a single pod. If multi-pod is already used, remember we already had this DP TEP, so we will continue to use this DP TEP. If single pod, the end user must define this data plane TEP, right? It won't be used as is, we're going to see, but because later on, user may have vPod, one pPod, and then add the second physical pod later, we don't want to mess up with those addresses, so at least we make sure that, that you have already those addresses deployed. Yeah, it's advertised as a /32 in the one, so typically it doesn't have to be part of the external TEP pool range because it's advertised as a /32. It can be basically anything. Okay, and then the ucast ETEP, which is basically an IP address, anycast IP address that is shared by all the spines. And this is this address that will be used as a destination for all known unicast traffic coming from vPod, right? So that will be, we'll see how it works, but basically we're doing a route map inside the vSpine so that we rewrite this data plane TEP by this one, right? So that the next hub for vPod in the pPod will be this unicast ETEP, or for this pod, this unicast TEP, right? So essentially this is the destination for unicast traffic from there to there, and in the other direction, obviously this would be the source traffic, the source address for the traffic. Again, it's allocated from the external TEP pool range, right, automatically for you. And then last one, but not least, we've seen that from pPod on the one side to vPod, we have headed replication. Right? We don't want the network admin to deploy multicast in the vPod network. But in multipod, so coming from vPod talking to multipod, you already have multicast, right? Because this is how you deploy multipod by default. So here we are adding a multicast TEP that will be used as a destination for all bump traffic from any vPod to a full site this time. So the multicast TEP will be one single address, not for one pod, but for the entire site, right? So today, obviously, it's a single site because this is what we support with vPod. But when vPod will support multiple sites, you will have another one, for a second site. Okay, hopefully it was not too complex now, but at least you have the slide. Now, if I ask you to repeat, probably you won't be able to do it. Also took some time for me to digest all that. But yeah, at least it allows us to satisfy any requirement in terms of customer network, because originally we had planned, let's assume that the original physical TEP pool is routable, but in fact we had many customers that said, yeah, no, you told us that it could be any network, so it's your fault, fix it. Right? So this is how we fix it. So as a side note here, when you deploy a BD into vPod, so typically it means you create your BD, so you have an AV VMM domain in vPod, you attach, so you create an EPG, attach the VMM AV domain, so the vPod AV VMM domain to that EPG, and that EPG is living in a bridge domain. This bridge domain settings will be disregarded when it's tied to vPod because we implement a hybrid proxy mode in vPod. So basically what that means is if destination can be L2, L3 is unknown to AV, so remember, the real leaf, the full-fledged leaf, is AV, it's not the vleaf, right? vleaf is just opflex in one route, right? Thinking this way. So if destination L2, L3 is unknown to AV, first of all, what will it do? Like, it will connect or query the CRUB database. What happens if the CRUB database EP entry is not present? So one copy here will be sent to, from the local AVE attached to the VM, will be sent to every AVE. So we're not using hrep, right? It's just AVE will send the frame to every AVE locally, so no hrep destination. And on top of that, because remember, it's a context of multipod, not multi-site, by default, all the BD are stretched, right? So one copy of the packet is sent to the physical pod multicast external TEP, right? The one we have just mentioned, that is on a per site basis. The receiving, so let's say it's this one, anycast address, right? So it can be this spine. And then the spine, it will do like the classical multicast path for BD flooding. So we'll pick up the corresponding FTAG tree, send it to all the leaf, and then the leaf that has effectively the bridge domain programmed will basically transmits the flooding to the whole BD, right? So each pPod replicates to all leaf in the pPod, and in the situation where the destination is known, then we don't need to flood. There is the packet is directly going from a VE tap, right, to the physical tap on the leaf, right? Make sense? So bump is going to the spine doing multicast to all the leaf. Traffic is known, AVE is directly sending to your physical leaf. Okay? A couple of other requirements in terms of the IPN. So it's not managed by EPIC like in a normal multi-pod configuration. We don't mandate any specific protocol within the IPN. You don't have to configure to connect all the spine to the IPN. But as multi-pod, you need OSPF between the spine and the IPN. And of course, you need to configure the DHCP relay because, so both in the IPN, right, and also on the gateway, right? I mean, every hop basically needs the DHCP relay because every leaf, virtual spine, needs on a DHCP discover, DHCP request, need to be forwarded back to the physical APIC in your main data center. This is what, yeah? Okay.
Round trip time with the same constraint that we have physical.
Yes. Okay. So the question is, how about latency? So it's just now, just in time. It's about, this is the latency between virtual spine and the physical spine, which is a bit more, right? Because I think multipod today is 50 millisecond. Here is 150 millisecond latency. And we need obviously the 50 extra byte for the external encapsulation, so on top of your existing user traffic. Right? Okay. So how are we doing with time? Half an hour, it's okay. So a quick word about vPod discovery, the process itself. So step 0, the prereq is that the tap pool has been created for vLeaf, vSpine, and AVE, which is part of the wizard, and we're going to have a quick view on the wizard. What are the different steps? So once vSpine, vLeaf images, so virtual machine has been deployed, you put them up, what happens? Right? So vSpine, vLeaf, we send DHCP discover, right? That's step 1. Step 2, we have the gateway there that sends the request back to APIC. APIC will allocate IP from the tap pool and send also the gateway information, right? Because the vLeaf, vSpine needs to find a way to configure the default gateway so they can talk back to peer with BGP, right? So APIC allocates IP from tap pool, sends gateway information. The gateway then forwards DHCP response to vSpine, vLeaf. vSpine, vLeaf configures IP and set default gateway, so within the virtual machines. Then certificates are generated, and you will see that even before you deploy vLeaf or vSpine images, as you go through the wizard from an infrastructure perspective, you will see already in the Fabric membership folder, you will see 2 vSpine, 2 vLeaf that will appear as undiscovered, right? And as a physical leaf or physical spine, APIC needs to sign certificates, and then you can validate that this is a valid, valid component, valid node within your Fabric. Exactly the same process there. So we need to generate certificates and sign them by APIC. And once the vSpine vLeaf has been discovered as Fabric components, then the vLeaf downloads the tap pool range for AVE, right? Because remember, for AVE, when you're going to deploy AVE as a second step, AVE won't send DHCP request back to APIC because it's not 4 AVE that you will have. It's probably maybe 10, 20 or more. So you don't want all those requests to go back to APIC, and that's also the data plane, data path. What happens if you lose connectivity between your physical site and your vPod, right? So we want to manage these addresses locally. So vLeaf downloads the tap pool range for AVE. And basically, AVE, we expect people to place them in the same large subnet, right, as a vSpine, vLeaf, but it's not a strict requirement. You can have AV living in its own subnet, right? So IP address managed by the virtual leaf, or you can just have everything into a single subnet. So vSpine, vLeaf, and AVE, which is obviously much more simple, right, from a management perspective. Okay, so how about now the deployment process? So first of all, as in vPod, you need to deploy the infrastructure component. So that means you need to implement the, so here I'm showing the deployment with, so you go into the Fabric view, right? You go to Quick Start, you will see the vPod wizard. If you already have multi-pod, it won't configure, so this side on the left is configuring the IPN facing interfaces, right? And on the right is configure OSPF and BGP. But if you already have vPod, you don't need to do this. It's already there to begin with, right? So as an option, obviously vPod, if you have a single pod, it will go through, the wizard will go through the configuration of OSPF and the interfaces between the IPN and the physical spines portion, right? Then the second thing, so first thing is to configure multi-pod type of connectivity to the IPN. Right? If multi-pod is there, you directly go to this stage. So you need to configure the external TEP for the physical pod. Right? So the routable TEP, this is the second step. So the only thing you need to give is, so here you can see I've got two pod 1, pod 2, physical pod. I've got the internal TEP pool, right? The one that was deployed day 1 for EPIC. Now I'm specifying a range for external TEP, the famous and hated, or I just hate it, external TEP pool. Then we have the data plane TEP. So remember what I said? I said that if you had already multi-pod configured, we will be using the one that is already there. So this is not something you have to worry about. If it's not there, you can pick any IP addresses, /32, that would be advertised into the IPN. And then, this would be the most important one. This is the unicast TEP that is present as a unicast address shared by all the physical spine from a physical pod that will act as the destination for unicast traffic coming from vPod to physical pod and as a source from physical pod to virtual pod. So this one is quite important, right? So, but again, you can use default there, and the wizard will just automate this for you, right? If you don't have any, if you don't want to pick any particular IP address. Okay, this is just what I explained there. So this is now the third step. First step was configure, if you don't have multipod, physical spine interfaces, OSPF, BGP, right, for multipod. Second step was the routable TEP pool. Third step now is configuring vPod TEP pool, right? So again, as in multipod, you will have to define the pod ID. So here I put 5. The pod TEP pool, and as I was explaining, you just pick like, I pick like what, /22. Out of this one, I pick like the last 8 or 7 addresses as /29, and this one basically will be responsible, that's the user reserved, where you will configure your default gateway, right? So here, that's the gateway IP address that must be part of this reserved pool. And then the other one that will be part of this one will be the vSpine and the vLeaf, and you will remember the OHSRP address if you want to use them, or DNS server, right? So this subset. And the rest, as I was saying, will be for AV. And the last one is the heritage from multipod will be the data plane tab, which is just used for multicast, right? We won't see it in the data plane for all the packet work. And now, basically, this is for TEP, and this is for virtual leaf and virtual spine IDs. So as any node, what you have to do is configure an ID, so 501, 502, configure the node ID for the vSpine, the router ID, which is also part of, as I was saying, this range there. So 248/29, you will find 250, 251 are part of this. And you can just leave it blank because, except if you want to use another router ID. And that's it. You can just use the default for BGP. If you untick default, you will be able to specify like a password for BGP for more security, right? That's it. And basically the last, so now what we have done so far, IPN configuration for, physical spine and OSPF configuration for the IPN connectivity. We have configured external TEP for our physical pod. We have configured virtual TEP, spine, and virtual spine and virtual leaf IDs for peering back with the physical data center, physical pod. And now the last step is now we need a VMM domain at some point. We need to attach virtual machine to something, to a VMM domain, right? And this is what the wizard lets you do. So if you go through this, basically what it does is you create a new VMM, but not a VMM based on traditional VDS. It has to be an AVE VMM domain, where basically you just specify the vCenter name, the VLAN range. The VLAN range is used internally because obviously we have VXLAN across the board. Then the name of the vCenter data center object, vCenter credentials, multicast for basically your VMM domain for just bump traffic, the fabric-wide multicast address, and the DVS version. So basically, it's nothing more but a VMM view, right? It's classic VMM. You can do it manually as well. You can skip this step there. But then when you deploy AVE virtual machine, the prereq is that the AVE VMM must be deployed before. The vCenter plugin, we're going to see that AVE is being deployed by the vCenter plugin. It won't let you deploy AVE unless you have an AVE VMM domain that is already being created. So you can do it there at this stage. So yeah, that's basically it. So without leaving APIC in a couple of just tab and screen, you can deploy the whole infrastructure, right? So you will see at this stage Fabric nodes as undiscovered. But what is missing now, you need to deploy effectively you need to deploy the virtual machines, right? So this has prepared for all the addressing. Now what is left is to deploy the virtual machines, right? So basically, I didn't go too much in detail in that section because I don't want, 20 minutes is okay. So I didn't have time to go too far in the AV deployment. Well, I'm doing it Friday if you're interested. But this is the process. You download vPod and AV images from CCO. You create a content library in vCenter, which is basically a repository internally on a shared storage on vCenter. You go here so you have to install the vCenter plugin for ACI, or the ACI plugin for vCenter. Once it's there, you will see the option to install AV, and it will scan the content library to propose you a particular image. So you can download multiple images, and this is how you would do the upgrade as well. Just download all the images there. And for vSpine, vLeaf, this will be the one on the top. So you select the version, the management interface, the infrastructure interface, the data store, the APIC passphrase to install them. So it's just when you have finished the vPod wizard, so you are given an APIC passphrase. It's valid for 5 minutes, so which usually is not enough. So if you go to, I think that's the APIC wide fabric settings, there is a new section that is APIC passphrase, right? So you can just copy paste from there. Deploy vPod, so it will deploy those 4 virtual machines, so there's nothing more to do. And then the last component, obviously, is AVE. So with AVE, it's a bit different because we need to have one AVE per host where you want to deploy the AVE VMM domain. So if you have like so today we support 32 hosts in the vPod vPod VMM domain. It means that we have to install 32 virtual machines in this cluster. But to facilitate this, what we have is with the plugin, again, you select the AV image, management port group, data store, and before that you select the cluster when you want to deploy it, right? And then install or upgrade AVE, and it will deploy AV within this cluster, right? So once this has been done, what you can do is start associating EPGs with that VMM domain, and you will see a new POR group that will be created into your VMware cluster, and job done, right? At this stage, you can obviously start extending ACI policies, and you can even do more. You can also, let's say if you want to extend your cluster, right? You have your vPod cluster on a data center, you have your ACI fabric with also a VMM domain. It can be the same AVE VMM domain across the board, right? Except on the one side, you will have AVE standalone, where you have physical ACI fabric. And on the other side, you stretch your cluster to an environment where you don't have ACI. So it allows you basically to do a VMware stretch cluster across the board. So in a data center where you don't have ACI, and in a data center where you have ACI, right? So this is how you can map those constructs together. Or, as an alternative, you can limit the AV VMM domain to your vPod environment and have another EPG, or the same EPG, sorry, in your physical environment, and you attach it to another VMM domain, right? So you have single EPG, 2 VMM domain attached, and then we'll just push the policy and the POR group into both environments. So in AV on the one side, let's say in VDS, normal VDS in the other side, right? So all this becomes possible, right? And by default, because this is a multi-pod context, every single bridge domain is stretched with BGP as a control plane. Okay, no? Don't like me anymore? Okay, just start. Restart it. Okay. Last section, packet walk. So now we've been talking about the control plane, data plane. We have 20 minutes left, which is good. I'm going to describe several use cases between single vPod and one pod, vPod, different, multiple physical pod, unicasts, broadcasts, everything, what's happened in the data plane, right? So let's start here with H1 wants to talk to H2 within a single vPod, right? Bridge traffic. So first of all, H1 generates an ARP request. Destination MAC is BUM. Source MAC H1, target IP H2 IP, right? So as the ARP goes into AVE, AVE learns the endpoint information locally. Then, obviously, because we generate a COOP update, so we have the COOP database on the vSpine. So here, vSpine, vLeaf, I just merged them because from a control plane perspective, it's not really important. As I said, vLeaf is just for one route. So COOP updates, and we also export to BGP, right? Which means that we keep synchronization between physical spine and virtual spine through BGP, as I was explaining, as a way to synchronize this database. So then a packet is sent also to, on the one side, so number 3 here. This is an ARP request. So we need to flood, but flood everywhere, right? Although we don't want to reach this site, it's multi-pod, so we need to flood. So first of all, this local AVE there will be responsible to send the ARP request to every single AVE in that particular vPod. So not using hrep, just using AVE normal way of transmitting packets, right? So every single AVE locally. At the same time, because again, we are in a multi-pod type of environment, we also send the packet to what? To the multicast TEP, routable one, of the pod that is there. But remember, it's common for the whole site. So if you have multiple pods, in that site, it's the same, the same unicast address. Yeah, question?
To enable optimization at bridge domain level?
So the question is, do you enable any specific setting on the bridge domain? But the answer is no, because remember, we disregard bridge domain setting on AVE. It has its own way of managing flooding. So you can configure any configuration basically on the bridge domain we won't look at it. We'll just implement the vPod way of flooding, right? Which is basically this, right? Replicate locally and then use the multicast step. So no need to optimize anything. So yeah, it's sent to multicast step. Obviously, on this side, because we have sent a data packet, we learn based on data plane. We update the local AV from H1 is mapped to L1 on this side. And at the same time, right, in parallel, we send the packet, so the multicast tab there is then responsible to use the BD GPO, right, so the multicast group, to send locally in that particular pod to send the frame to every leaf. So use that particular F tag so that you can flood this ARP to all the leaf that have an interest in that multicast group. So basically, then we update only, right, the leaf on their local table where the BD exists. Right? So the frame was flooded everywhere, but only this guy here will update its local table because it's the only one that has the BD deployed. Right? So L3 VTEP mapping is updated because H3 is in the same BD as H1 and H2. Right? Nothing there, so I don't update it. Then, eventually, on this side, right, the packet reaches H2. So how about the return path? So first of all, now H2 respond to this. It's respond as a unicast ARP reply. So source MAC H1, destination H2, same for IP, right? So obviously, the assumption was that it was never learned locally. So the first thing, because we learn based on unicast as well, right, on the data plane, ARP on control plane, because this is ARP, we learn H2 is located locally at L2. And then what happened is that because we already know that H1 is in L1, we just send the unicast traffic to that tunnel with AV tab as a destination. Job done, right? So obviously, when packet arrives this AVE, we also update. H2 is located to L2, and then packet is transmitted to H1, right? And then we have a fully populated table and synchronization everywhere. And on this side, you can also notice that we are aware of what's happening in vPod, right? So now, same thing, but H1 want to talk to H3, vPod to pPod bridge. So the foundation will be exactly the same, right? So typically, local endpoint learning, we update COOP there. We have BGP updates on the other side. Then again, we do the same thing. We send locally. We send it to the multicast tab on the other side. So then we update there the table on AV based on the ARP, on the flooding. And on this other side, again, as before, we send it to the GPO multicast address. Then multicast will be responsible for transmitting this frame to all the interested leaf. VTEP is mapped, table is updated because this leaf has the BD deployed. This one hasn't, so we don't update it. And packet reaches H3. So unicast, ARP, reply, same thing happened. So we learn the assumption again, we didn't know about H3 on this directly connected leaf. It's updated. The COOP is updated locally. On the other side, the COOP is also updated, but remember, this is where we do the route map, where you need to change, instead of having like the DP tab, right, we use the routable unicast tab so that this guy here becomes the next hop, right? So next hop for vPod becomes the unicast routable data plane tab, right? Because the other one is not advertised. Remember, this is this thing where we need to have this external tab that must be routable. So we do basically a route map that allows us to change the entry there, right? So that traffic coming back from the vPod to pPod will be destined to something that is reachable. Right? Then, after the updates, because we know already that H1 is in L1. We already know. Destination is no. So tunnel from physical leaf to AVE directly, right? As you said that. And then, again, here we have the VTEP table that is updated, but still with the physical pod unica step. And then packet eventually reaches H1. Question?
So the physical spine root database don't have the unicast step. It communicates directly with the API.
Yeah, so the question is, the physical spine doesn't have the unicast step. No? So the answer is no, because on this side, H3 is local, right? So H3 must point to the physical tap of the leaf. H1. No, at this stage, H1, because there's no routable tap on this. There's a single tap, so we can do direct communication. We don't need to do this source NAT type of things, right? On this side, we need to do this NAT, right? Expose this external routable tap. So therefore, we need to change something here. But this side here is like brand new, right? So we can use the normal. We can use the single tap we have defined there. Because by default, we warn you, this must be routable because this is what you are going to deploy. So the vPod tap pool is by default routable, right? We don't want you to deploy two tap. We already do it here. We don't want you to do it here, right?
Why not do the same in the physical part instead of doing this NAT, having the communication direct from APE to the...
Yeah, so why you don't do it in the physical pod? So basically, instead of using the pPod unica step, using the normal data plane tap. Right. Yeah, it's because our assumption is that here, the original tap pool from your physical fabric is not routable, right? Okay, because that's the foundation why, because day one, and this is our mistake, we told people, look, you pick any IP you want for your tap pool, but at some point so this is what customer did, like they took public addresses, right? So it can be anything, but in reality, I mean, if you manage all the devices here, IPN, WAN, etc., you can create VRF and job done, right? But sometimes you cannot control the range there. You don't want to overlap. So this is why we have created this routable external IP. But in my opinion, we should have warned people that, look, we are innovating at some point, and maybe we want to extend this step pool to do some things smart. But yeah, we didn't plan to do smart thing, but it happened. So we did smart thing, I think. So yeah, this is why it's required. And the trick there is basically we just do a route map there to change the entry, right? So that this IP there is now reachable. If we don't do this, and we replace by the basic data plane tab, it's basically not reachable. It's not advertised. It's not supposed to be advertised, right? Obviously, you can advertise if you want, but yeah, that won't help if you cannot manage them. Now, the only difference between routed and bridge traffic is this one, right? So it's similar to previous, but destination MAC is just the BD MAC. Oh, with one caveat, that is, I mean, it's currently by design. You cannot customize the BD IP in vPod. Right? If you do this, it will drop traffic, right? So if you deploy vPod, use the default MAC address. Don't change it, right? I think we have currently a bug open for this, but yeah, it's quite unfortunate. But yeah, you can just use the basic MAC address of the fabric. And obviously, the second thing is, if we don't know the destination, if you cannot reach, if the destination is unknown, because we route traffic at the first hop, which is in AV, right? So for routed traffic, destination fabric MAC reaches AV, we route at this level. If we don't know the destination, then we can glean. Then we can send the glean packet in the network, right? And then it will be processed in the normal way, right? Okay, now for the last 5 minutes, it's just vPod to multi-pod, pPod, right? So in that case, imagine H1 to H3, So H3 is in there, pod 3, but I also have pod 1. So I'm sending a ARP request. So this is a broadcast. I'm learning the mapping H1 is to L1. Coop update, again, so update locally on vSpine. BGP to update the Coop database everywhere on both pods. Then you have packet is sent to the multicast TEP, but also L2, right? So it's sent there. But again, it's sent, oh, actually this one there, I should have put it there because this is the multicast TEP is on this side, so that's a typo of my part. So this should be there, right? So destination of the traffic will be the multicast TEP, but remember, it's shared across all the spine for a particular site. So here, as an example, I've used this spine there, which is not on this pod, right? But depending on the selection, it can be this spine there, right? But I wanted to, yeah, for this example, let's assume it reaches this spine there, right? So obviously on this side, mapping is updated, and on the other side, then again, it's sent locally to the GPO, but because this is multipod and we use multicast, then eventually it will also reach the second pod, right? So it's send to any cast address. This guy then receives the frames, use the BD multicast group address to transmit the flooding, and will flood to every leaf. And then again, as usual, the local updates of the leaf will be for the leaf that are interested, that basically have that BD defined. Yeah, question?
Sorry, I'm not sure if you mentioned, what's the maximum number of vPods, and what happens if they're various? How does the traffic work between them? Are you going to cover that use case?
vPod to vPod, no, but it's basically the same thing, right?
Is it going through the physical pod, or can it go there?
No. So the question is, first, the scale of vPod. So number of vPod today is 6 hosts, per vPod 32 nodes. But the scale is currently published. And the other question was, what happens from vPod to another vPod, right? So between ingress traffic is like when you get a frame from pPod. Egress traffic from vPod is exactly the same as if you were talking to physical pod, right? So it's exactly the same as here, right?
But would they be?
No, you don't go. So you don't go through physical pod, right? Yeah, vSpine to vSpine, right? We don't pin traffic to physical pod. Yeah, and then eventually, so after VTEP table update, packet is sent to H3. Return traffic, so again, we learn locally H3 is under L5. This is unicast. And then we know the destination. We want to talk to H1 that is located on L1. And obviously, we have the H3 to L5 that is updated everywhere. And then because we know the destination, this is unicast, we do a direct tunnel between the physical leaf L5 and L1. And last step, L1 VTEP mapping is updated, but again, we do this route map to modify the next hop so that it's something that is reachable. Right? And then last step, packet is sent to H1. Now, this is the challenge. Currently, what do you do if you want to have a physical host? That's 2 minutes. Okay, cool. Last slide, one of them. So, does anyone know? Do you want to guess? What do you do? Let's say you have a physical host in vPod. Right. Okay, so what you have to do today, right? So we're working on a solution, but basically, as I was saying earlier, the layer 3 out for vPod will be on pPod. There's no local layer 3 out. And basically, what you need to do if you have something physical there is create a layer 3 out from this leaf, peering with a network there, attaching this host as an external /32, so external EPG, and then create a contract between this guy and locally, right? It means it will go. Currently, this is the only workaround because obviously vPod is for virtual environment. So today, this would be the workaround. But obviously, if you have loads of physical hosts in a remote data center, vPod is not the target. The target is remote leaf today, right? So this is the only workaround, fortunately. But we are working on something, right? Or engineering is working on something. I have some thought, but sometimes engineering just think I'm stupid. Maybe that's the case. I don't know. I think sometimes, no, it's recorded. I shouldn't say anything. Okay, additional information. So in terms of licensing, I'm not a sales guy, so this is what I've been given. So for me, everything should be free. But yeah, that's not the case. So ACI Virtual Edge, it's licensed in vPod mode per workload, per hypervisor, basically. vPod, AVE in standalone I think is free. vPod will depend on the ACI tier license you have. I think there's a new premium tier that has been created that allows you to basically deploy anything. And on top of that, you will have a software license per AVE and per hypervisor, essentially, right? So it won't be free. So this one is not true. It's 32 because we've just updated with the latest release. It's 32, not 8, and that's it. But we don't sell VMware licenses that come with it. 32 hosts per vPod today, and 6 vPod per fabric, essentially. But we plan to increase those numbers as well, right? Eventually, at some point, maybe to have full virtualized ACI, but maybe our friends at VMware, they won't be too happy about this. Okay, and it's finished. So just the roadmap for you, for your information, you will have it in this, on the slide. So today, we don't have service redirection, we don't have micro-segmentation, and the idea is to support up to 12 pod, to have eventually full virtual APIC support, and basically extend the concept to Hyper-V and KVM as well, right? Okay, it's, with this, thank you for staying until the end. If you have any question, just feel free to catch up with me just there, right? Thank you.